Hello everyone, this is Mr. Couple. In this video, I'm going to show you how to derive the distance equation. We'll do that by considering a person walking along the sidewalk. The sidewalk is evenly spaced tiles of intervals of 1 meter. And as the person walks, we'll take pictures every 1 second to mark the location of the person during this journey. The first question I want you to consider is, identify whether this person moves with uniform motion or accelerated motion, and justify your answer. Pause the video to answer this question. The way you can tell that the person is moving with uniform motion or accelerated motion is that uniform motion means constant velocity. And as the person is walking, we notice that in equal intervals of time, 1 second intervals, the person travels equal intervals of distance. This means uniform motion. The motion is constant and uniform. The intervals between each time are equal in distance and time. This is uniform motion. We'll talk about accelerated motion next week. Determine an expression for the speed of this person. So the first thing we want to think about is, well, let's consider the distance. So we know the speed is distance over time, and we learned that in a previous lesson with Mr. Schmitz. And so what we can say is, well, we can find the change in position of this person by labeling the final position and the initial position. We're making these measurements to the front of the person, to the front of their foot, where it reaches the line. And this distance is called the displacement, or the change in position. And that's the distance that we plug into this equation. So we can say that the change in position is equal to the final position minus the initial position, because that's how you calculate change, by taking the final quantity subtracted by the initial. What about the bottom of this expression, the change in time? We'll do the same thing. We'll consider the final time reading, and we'll consider the initial time reading. And the change in time is simply the difference between these two quantities, the final time minus the initial time. Now, this is a really complicated looking equation with all these crazy subscripts and symbols everywhere, so we should probably try to simplify things a little bit. The easiest way to do that is to just decide, hey, you know what? I'm going to start measuring from 0 seconds. And we're going to start measuring from 0 meters. And so we make that our reference point, that very beginning is the 0 seconds, 0 meters. And then that means the ending point is simply t, the time that has passed, and x, the distance that's been traveled. Because the final quantities will just be equal to the time that has passed. Because if you take the final and you subtract 0, well, then the final is the total. So the change is equal to the final. So that's what I'm trying to get at there. It's like when you make these things, these initials go to 0, then that means that the finals are the changes. And so we can rearrange this equation so it looks just like this, x over t, because the initials have gone to 0. And we're defining, the way we've defined it with this as our reference point, the finals are just equal to the changes. And so we end up with this much, much simpler version of the equation, which just says v equals x over t. And in this case, x is the distance traveled, and t is the time interval, or the time it took to travel that distance. So here's a way of looking at it. If we know how far a person has traveled, and we know how long it's taken, then we can find the velocity, or the speed, by simply doing the distance divided by the time. And so this is the expression for the speed of the person. Next question. Algebraically rearrange this equation to solve for x. Solving for x means get x by itself. So the first question is, how can we get x by itself? What do you need to do to get x to be by itself? Pause this video and respond. Well, we need to do some algebra. So we need to think, what do we do to both sides of this equation to get x by itself? The answer is you multiply both sides by t. But why does this work? So I want you to explain the reason why this works. So here's what happens. First, you need to recognize that both of these quantities, v and x over t, that they're equal. They're the same thing. And so if we do the same thing to both sides, multiply by t, then both sides of this equation are still equal. So we haven't changed anything. Even though we've added a multiply t on both sides, you haven't changed the equation at all. Both sides are still equal. Next, if we rearrange this part, so let's look at that one more time. So if we rearrange the t to instead being divided by the x, but instead being divided by the t, you can very easily realize that that is just 1. And x times 1 is still just x, because multiplying by 1 doesn't change anything. And so that's the reason why this works. We're able to basically move the t to the other side of the equation by multiplying both sides by t. We've isolated x. And the result is this form of the equation, which we call the distance equation. Question 4 is to summarize the distance equation. What that means is tell me the name of each physical quantity that the symbol represents and state the units of measure used to measure each quantity. Take a moment and go fill in this table on your Google Doc. Pause this video. Well, x stands for distance. And this equation says the distance is equal to the speed multiplied by the time. You might not remember this, but if you have two letters that are next to each other in an equation, it always means that they're multiplied by each other. And the units of measure, well, distance is meters. You'll notice that I put this in brackets. The reason is because otherwise it might get confused with mass, with a symbol. So we put it in brackets to specify that this is indeed a unit of measure. Meters per second for speed times seconds for time. And so don't forget that the M stands for meters, the M/S is the meter per second, and the S is the second. Now something really cool happens here. At every step along this summary, these are all still mathematical expressions. And so check this out. If you take meters and you divide by seconds, and then you multiply by seconds, you get back to just having meters, because division and multiplication are inverse operations of each other, and so they undo each other. So dividing by seconds and then immediately multiplying by seconds just gets you back to meters. So even though it doesn't look like it, a meter per second times a second is a really fancy, complicated way of just writing a meter. And so it's very important to remember that whenever you have an equation like this, that there's units of measures and physical quantities behind each of these symbols. And that will be very important in a minute when we start to solve some example problems. I'll see you in the next video.